Hey everybody, and welcome back to Linear Algebra Online. So the plan for today is to talk about a really important concept in linear algebra, probably the most important concept, and that is eigenvalues and eigenvectors. So I wanted you to watch the 3 blue, 1 brown video before you see this. So if you haven't done that yet, go and watch the 3 blue, 1 brown video on eigenvalues and eigenvectors, because there's a lot of beautiful visuals that relate to kind of the more specific mechanics that I'm going to talk about in this video. So with that said, let's get into this. So the vectors that change, let me back up. A lot of vectors change under a transformation, but the ones that only get stretched, squished, reversed, and stay completely invariant or mean just don't change, those are what we call these eigenvectors. So most of the time, right, when you apply like a matrix A to a vector, it just gives you like a whole different sort of thing over here with, moves that vector somewhere else. But what an eigenvector is these things X where after A is applied to X, you just get like a scalar on X. So, if the scalar is 1, that's like the invariant one. It just literally doesn't change. If you stretch it, maybe the scalar here is like a 2, squished, it could be like a 1/2, or reversed, you can make it like negative, and then you can also be like -2 or something like that. So those kind of vectors are what we call eigenvectors. And the amount by which it's stretched or squished, that's the lambda thing, is the eigenvalue. And this is kind of the formal notation that we see with eigenvectors and eigenvalues. So, you want to look at this as matrix operating on vector. It's kind of like it's a function with the input of x. And it's saying that you do that, and the only thing that happens is it really scales x by some number. And that number is the eigenvalue, lambda. And maybe I should actually write that. So this is a lambda, and that vector x is an eigenvector. So just to kind of show this, I think I'll just actually do one of them for time reasons. But these are eigenvectors for this matrix. So if we see here, 0.8, 0.2, 0.3, 0.7, and we times that by 0.6 and 0.4, right? If we do this multiplication out, we get that. You can literally just test it. Multiply this times this, you get 0.6, this times this, you get 0.4. And so what this is it's saying A times my vector x equals, 1 times my vector x. And so that has the structure here. This is a case where the vector 0.6, 0.4 is invariant. It doesn't change under the transformation given here in A. And you can see the same thing. If you do A times x2, what you're actually going to get is you're going to get 1/2 of x2. And I'll let you kind of do that one out just to see it. But that's all eigenvectors are. They are just things that basically change in very simple way, and the simple way is that they're just a scalar of the original vector after the transformation, which is pretty rare. If you think about it, most of the time, if you do like a rotation or something matrix, and like you have the vector like I hat here or something, if you do a rotation by like 90 degrees or something, you might just take I hat and you move it to J hat. And so it moves, and so it wouldn't be an eigen vector. There actually are eigenvectors to the rotation matrix, but we're going to talk about that later. So that is what they are, okay? They're just things that change in a very specific way, and the eigenvalue is the amount by which they change. All right, so this question just says, show that 5 is an eigenvalue for this matrix, and find all the eigenvectors for this value. All right. So if we do this, we basically, I'll say something about this other line here in a second, but we basically need to show that like a times x equals 5 times x. Like find the things like x, the vector x's, that do that, like the structure of them, okay? So if I just kind of do a little bit of algebra here, right, I could move this over, and then now that's equal to 0. And then, well, 0 vector, I should probably do that. And then I'm going to take like the vector x out on the right. So I'll have a minus 5 times the identity matrix times the vector x equals the 0 vector. And so we basically just have the structure now to set up a matrix to help us solve. So, this part, a minus 5 times I, would just be -4, 2, 4, -2, right? Literally just using a up here. I guess I didn't really say that, but I'm calling that a. So that's a minus 5i. And then we are multiplying by, just call it like xy, that's my vector x. And we're setting it equal to this 0 vector, all right? And so it's basically a, RREF problem. So we're going to take -4, 2, 0. Whoops, 4, -2, 0. And if we RREF this thing, we get 1, and then -0.5, and then 0, 0, 0, 0. And from that, right, we can see that like x equals 1/2 of y. And so if we just like let y equal t, right, then we would have basically this vector xy thing just looks like 1/2 t, and then 1, right? And so this is the structure of all the eigenvectors for this value given this matrix, okay? And so the span of these eigenvectors, which is really like, the set of all these linear combinations here. So that span with the 0 vector, so formed with that, forms a subspace that we call the eigenspace. And I'm going to talk about that here in a second. But that eigenspace is a very important thing. And we talk about the eigenspace of specific eigenvalues. And that's like an important thing to note. So there can be a subspace related to the eigenvalue of 5. And there can also be like a subspace related to a different eigenvalue. So that is like an important distinction. It's not like the matrix has just like one of these eigenspaces. You can have multiple eigenspaces for one matrix. All right. And so I'm actually going to use this kind of example to just talk about eigenspaces in a second here. But geometrically finding eigenvectors is important too, just kind of thinking about like what's happening. So if you have this matrix, right, this represents where I hat lands, and this one represents where J hat lands, okay? And I hat is landing where I hat is. And then J hat is moving to 0, -1. So if we like take a picture, just like a graph here, we have that I hat is landing right there where I hat is. But then J hat, which is up here, is going to 0, -1. So J hat is landing over here, okay? And if you think about that, then that means that like all these vectors that are like on this axis, they basically won't go anywhere. But the ones that are like above are flipping over the x-axis. So this is like a vertical flip matrix is basically what's happening here. All right. And so the eigenvectors, the ones that stay in their span, which is really what an eigenvector is, right, would just be the things on the axes, right? Like if you take, get like a different color here. So if you take like this vector, right, it's basically going to end up over here, but this, we'll just here, let me do, so after the transformation, it'll end up, I'll make it dotted like that. But only the things that are in the span of that vector, that line right there, would be like if it landed in that line, I should say, then it would be an eigenvector after the transformation. But that's not what's going to happen. It's going to move outside the span of that vector, so it's not an eigenvector. So the white one is not an eigenvector, but like, if I take, something like this, that vector literally is just going to stay put. It's not going to flip over anything because it's on the line of symmetry. And so that orange one would be an eigenvector. It has an eigenvalue of 1 because it doesn't scale or flip or anything. When we talked about j hat moving down here, that is also an eigenvector because it flips, it stays in its span of the original vector. Its eigenvalue for j hat would be -1 because it's just going to flip around but not stretch. So I think I've said enough there. The general result here is that what does the matrix do? Well, it flips vertically, and the eigenvectors are, so this part are any vectors on the x or y axis. And that's it. So those are what the eigenvectors of that problem look like. All right. And then I want to talk about the eigenspaces of this matrix. So formally, this is the definition of an eigenspace. So if you have an eigenvalue lambda for some matrix A, then the eigenspace we denote, again, it's specific to an eigenvalue. So we would denote like E sub lambda. And it's the set of all eigenvectors of A with eigenvalue lambda together with the 0 vector. Okay. So in this problem for this matrix over here, you basically have eigenspaces that are formed from these kind of two vectors, okay? And so we have one eigenspace, so I'm just gonna kind of call it E eigenspace 1 for right now, and because actually the eigenvalue is 1 for that, but the eigenspace for this green vector would be like the set of all linear combinations of really the of I hat, sorry. So maybe we'll write it this way. We'll do 1, 0. So basically I'm just saying that one eigenspace is the x-axis. That's what that is, right? It's the set of all these linear combinations of the basis vector I hat. Then there's an eigenvalue, and you don't really need to know why it's an eigenvalue of -1. I mean, we kind of talked about it already, like, actually, I think I would say you should know it, right? But basically, I'll talk about how to calculate eigenvalues eventually, which is what I'm thinking about right now. So you don't necessarily need to know how to like do these intuitively right now, because I'll show you soon how to compute it. But if it flips like that, but doesn't stretch, then it's a eigenvalue of -1. And so that eigenspace would basically just be the things in the span of 0, 1. So more or less the y-axis, right? And the 0 vector is in there, right? And you need the 0 vector because of like subspace definitions, like down here. I just put this in to remind you. So the 0 vector is in there. It's on this axis and this axis. And then you can see that like if you add a vector like on the x-axis to another one or something, you would just get a bigger vector, right? I guess unless you added like a negative one over here, then it would like kind of balance out. And, you know, if you have a vector like on the x-axis, and you have a scalar like from the real numbers here, and you do that scalar times the vector, then it's going to stay on there, right? You just stretch it out or flip it or something like that. So these are what we call the eigenspaces for this matrix. All right, one last little conceptual kind of thing, and then actually the next video is where I'm going to really get into the nitty-gritty like computation of eigenvectors and eigenvalues. So just to kind of like see it in a picture, so take these two pictures here. These lines, these black lines are basically the just like the original vector x, okay, and ax is another vector, and it's the one in blue, okay. And the question is like, can you spot the like eigenvectors in the problem? So, you know, if I just take specifically like, oh, I don't know, how about this one, and then from it this one, right? So the eigenvector for this original vector x here, it just needs to stay in the span of that vector, which is that line right there. This is clearly not in that line. So this thing is not an eigenvector, because ax doesn't equal a scalar on the original one, right? And if you go through and you kind of look around, right, all of them do this, right? So this thing is a problem that has no eigenvectors, okay, which can happen. And this one over here, though, so, you know, if I take, just as another example, let's do like, let's do this, and then like, I think it's that one. You know, this, again, is the span of my original vector. And this is clearly not in the span of my original vector. It's like the matrix A has like, you know, stretched it out. It's bigger, and it's been like twisted and rotated. But if you look, and I think I'm going to show you the right ones here. So this vector, after the matrix transformation, just gets stretched out like that. And this one also gets stretched out like that. So, you know, these two vectors in here, this one and this one, are the two eigenvectors in that problem. But all the other ones, you can see like the one right next to it, it's just off, I think, a little bit. It doesn't stay in the line, in the span. So, big idea here. Eigenvectors are things that stay in the span of the original vector after the transformation. And the eigenvalue is purely the measurement of the stretch factor, right? And it can be 1, it can be negative numbers, it can be positive, you know, larger than 1, stuff like that. But that's it. These are like really important concepts, and you're gonna actually see some really important applications this year of these. But this is just kind of to get you started with the basics of what eigenvalues and eigenvectors are.